welcome all. So, in the next part or the lecture 2, I will also continue my previous introduction part, and I will discuss a few terms that will be used for this course. So, next thing that is very important is the relative density. So, it is also important for granular soil. So, relative density is the degree of compaction in the field can be measured by relative density. So, relative density definition is, so E max minus E, and the difference between the maximum and the minimum void ratio, and it is generally expressed in percentage. So, where E max is the void ratio of the soil in the loosest state, and E min is the void ratio in the densest state, and E is the in situ void ratio. So, based on this relative density, we can classify the granular soil. So, if the relative density is less than 15, we can say the soil is very loose. If 15 to 35, it is loose, and if it is greater than 85, then the soil is very dense. In between that, we have given other values also. So, that is why the relative density also very important parameter for the granular soil. So, next one is the Atterberg limits. So, these Atterberg limits are very important. So, we will use this term. So, there are 3 limits. So, as we know, the soil has 4 states. So, if you look at this, if you see this picture, the soil has 4 states, that is the liquid state, plastic state. So, this is the liquid state, plastic state, semi-solid state and solid state. So, now soil has 4 states, and the junction of each state has a limit. For example, that if you reduce the water content in a soil, so that means soil will change its state from liquid to semi-solid. Then if you further reduce the water content, it will go to sorry, if you reduce the water content, then soil will go from liquid state to plastic state. Now, if you further reduce the water content, soil will go from plastic state to semi-solid state, and if you further reduce it, then it will go to semi-solid state to solid state. So, liquid, then plastic, then semi-solid and solid. Now, that means the liquid limit is the water content at which soil changes its state from liquid to plastic, or vice versa. That means, if you add keep on adding the water on the if soil as in solid state, if you keep on add on water in the soil, that means from solid state to it will go to semi-solid state, then from semi-solid state it will go to plastic state, and from plastic state it will go to liquid state. So, in other way, liquid limit is the water content at which soil changes its state from plastic to liquid. So, that is the liquid limit. Similarly, we have the plastic limit, where the soil changes its state from plastic to semi-solid, and another one is the shrinkage limit, where soil changes its state from semi-solid to solid, or vice versa. So, it can be in the both ways. So, now if this figure is the moisture content and the volume of the soil water mixture, if you see that if you reduce the water content, then soil volume also reduces, but after the shrinkage limit, soil volume does not change if you further reduce the water content. So, these states are very important, and these limits are also very important. These limits we will use for our design purpose. So, next one is the hydraulic conductivity of soil. So, hydraulic conductivity can be written as we know the velocity of flow of water through a soil is equal to K into I. So, the K V is the Darcy's velocity and K is the hydraulic conductivity of soil and I is the hydraulic gradient, or that we can write del H, the pressure head, the head difference divided by the length of these 2 points. So, this is the direction of the flow. So, this hydraulic conductivity is also very important, and we have that. So, this hydraulic conductivity in the laboratory we can determine by constant head method, more suitable for coarse grain soil, and falling head method, which is suitable for soil as fine sand and silt. Now, the type of soil that we have a table by which we can get an idea that what is the hydraulic conductivity of different types of soil. So, this is the medium to coarse gravel, it is greater than 10 to the power minus 1 centimeter per second, and for the clay, which is the least, and that value is 10 to the power minus 7 or less centimeter per second. So, these values are the hydraulic conductivity values for different types of soil. We have the coarse to fine sand, silty sand, we have a silt, clay silt and silty clay. So, these are the ranges are given. So, next one that we will start the another properties that we have is for our effective stress, which is also very important. So, we will discuss about the effective stress part. So, effective stress is a very important thing, and when we calculate the stresses during our settlement calculation, then we will use this effective stress frequently. Now, what is effective stress? Now, effective stress, you can see that when these are the soil particles, and in between the soil particles we have water. So, when we apply the stress on a soil, then initially there will be a stress distribution among the water and the grains. So, for example, that means the stresses are shared by the water and the soil grain. So, that means soil, if I apply the stress, for example, if we have say a container and one valve is attached here, and this is a rigid support. So, this support is very rigid, and we have a spring here, and this is the water is there. So, here the water and this is the spring. Now, we are applying a load here on this piston. This is the piston where this is the valve. Now, if the valve is closed, then all the stresses will be taken by the water, because our this spring will not deform. So, it will as it is not taking any load or any stress. So, initially under this condition, when you have a container and water, you are not allowed to water to move from this container. So, initially all the stresses will be taken by the water itself. Now, if I in the next condition the same container, now what we are doing, that we are allowing this water to flow. That means, we open this valve. The first case, this valve is closed. Now, we open this valve and now we are applying this same load here. Now, what will happen? This water will start coming out from this container, and this piston will deform as water is coming out. So, this now this spring will start taking load or stress, and what will happen, this spring will deform and this total system. So, now this say this piston will come here. So, this is the amount of deformation of the spring. So, suppose this is the amount of deformation of the spring, this is del H is the amount of deformation of the spring. So, now what will happen, that this spring will start taking stress, and when the total water will dissipate from this container, then the total stress will be taken by this spring only. So, that is why now if I draw a graph, that is, this is the time t and this is the stress. So, initially at t equal to 0, the spring is not taking any load. So, this is the time versus stress distribution. So, this is the maximum stress or P max. Now, at time equal to t, as the spring is not taking any load. So, the maximum stress, the total stress is taken by the water, but at time progresses, these stresses are transferred from water to the spring. So, now if I draw the time versus stress distribution of the water. So, this is the time versus distribution of the spring and this is the water. So, we can see that initially the spring which is taking no load, then the slowly start taking the load or the stress, and water, the stress on the water will reduce as water is dissipated from this container. So, here this spring is representing the soil particle and water is the water in between the void. So, that means, if we apply the load on a water and if I do not allow this water to move, then the stresses will be taken by initially water. Then when the water start dissipated from this area, so that means all the stresses will be taken by the soil particle. So, the effective stress is the stress which is taken by the soil particle itself. So, that means we can write that the effective stress is the total stress minus pore water pressure. That means, the pressure which is or the stress which is taken by the water or the stress which is developed due to the application of this load. So, that means, that stress is the pore water pressure. Pore water pressure is U is the pore water pressure, and for the dry soil, as there is no water. So, all the stresses will be taken by the soil particle. So, effective stress will be equal to the total stress. So, we can move to the next part. That how I can determine the stresses at any point or effective stress at any point. So, these calculations will use number of times during our stress calculation in the foundation design. So, suppose we have a soil and this is the point A where I want to determine the stress, or rather than I should say the effective stress. So, effective stress is this is the sigma bar or sometimes sigma dash, sometimes we can use sigma bar also, sometimes we can use P dash or we can use P bar also. So, now we have a soil layer and where the point A where I want to determine the effective stress, it is at a height of h or at a depth of h 1 plus h 2 from the ground surface, and water table is at a height of h1 from the ground surface. So, what I can write that the first I will calculate the total stress. Now, the total stress will be the, so suppose this is the unit weight of the soil, or you can say this is the unit weight gamma bulk. Sometimes we in this course, if nothing is mentioned, then if it is mentioned the gamma, then you will assume that this is gamma bulk. So, if gamma is mentioned, that means gamma bulk. Otherwise, I will mention gamma dry if it is a dry soil, or gamma saturated if it is a saturated soil, or gamma sub, that is gamma saturated minus gamma W. So, here nothing is mentioned, means it is gamma bulk or gamma. So, that means here unit weight is gamma or gamma bulk. So, and the saturated unit weight is gamma sat. So, the total unit weight or total stress will be H1 into gamma plus H2 into gamma sat minus the pore water pressure. Pore water pressure will be H2 into gamma W. So, I can write that H1 into gamma plus H2 into gamma bar. So, gamma bar or gamma sub is equal to gamma sat minus gamma W. So, gamma bar is the submerged unit weight of the soil. So, as I mentioned that the how I will mention these, I will show the different unit weight, either gamma or gamma bulk, then gamma dash or gamma sub, then gamma D or gamma dry, then gamma sat is the saturated unit weight. So, this is the bulk unit weight, this is the submerged unit weight, this is the dry unit weight, this is the saturated unit weight. So, these are the different unit weights that we will use. So, the effective stress we can write that H1 into gamma plus gamma sub into H2. So, that is the effective stress at a point A from the ground surface, which is at a depth of H1 plus H2. So, next one is the compaction. Compaction is also a very important thing. So, there is two terms, one is the compaction, one is the consolidation. So, basic difference between the compaction and the consolidation: in the compaction we are basically eliminating the air voids, and in the consolidation we are eliminating the water voids. So, in the compaction we use the standard Proctor test to done the compaction, and we have the modified compaction also. So, here we determine the optimum moisture content and maximum dry density. So, you can see the here in this figure the solid volume, in terms of volume, the solid volumes remain same even after compaction, water also remains same after compaction, but air volume will reduce after compaction. So, because the here compaction we are reducing the air voids, and consolidation we are reducing the water voids. So, in the compaction part, if I if I show you the typical compaction curve. So, this is a typical compaction curve. In x axis it is water content, and in the y axis it is dry density. So, we have a curve, and from this curve the peak is given the maximum dry density, and the corresponding water content is optimum moisture content, and this dotted line is 0 air void lines or 100% saturation line. So, that means 100% saturation means there is no air void present in the soil. So, these are the this is a typical compaction curve. So, and this is the our the dry unit weight expression that we are getting from the previous expression that I have already discussed in the first class. So, next one is the consolidation. As I mentioned that there is two things, one is compaction, another is consolidation. In the consolidation also we are reducing the volume of voids, but here we are reducing the water voids. So, here this is a typical consolidation curve. So, this is this part, the first part is the loading curve and the second part is the unloading curve. So, you can see from this part, the first part, we will get a compression index, which is very important. This compression index will be required for the settlement calculation. So, this compression index is basically the slope of the straight portion of this loading curve, and the compression index is basically the difference between the void ratio. This is the void ratio, this is void ratio E. So, this is the void ratio and the pressure, this is the small k, this void ratio and pressure curve. So, this pressure it is in log scale, and so this is the difference of void ratio divided by difference of pressure in log scale, in log. So, that is the E log P curve. So, from there the slope will give the compression index. According to Skempton also, if I know the liquid limit of a soil, we can determine the compression index, and that is 0.009 into liquid limit minus 10. So, liquid limit value we have to put and we will get the compression index, or compression index we can determine from the E log P curve. We will do a consolidation test, and from that test data we get a E log P curve. We do it for the loading and we can do it for the unloading. So, we will get this the curve for loading and unloading. So, the slope of the straight portion of the loading curve will give the CC. So, now a term which is very important is the normally consolidated soil and over consolidated soil. Now, these two terms we use frequently for our during our design, that now what is normally consolidated soil and what is over consolidated soil. Now, if the present effective overburden pressure is equal to the pre-consolidated pressure or the maximum past effective overburden pressure, then the soil is called the normally consolidated soil. So, that means if the stresses that is applied on a soil is more than the stress the soil is previously experienced, then that soil is called as a normally consolidated soil. That is why the present effective stress is equal to the pre-consolidation pressure, or equal to or greater than the pre-consolidation pressure or the maximum past effective overburden pressure of the soil. And the over consolidated soil means if the present stress which is applied on a soil is less than the stress the soil is previously experienced, then that soil is called as a over consolidated soil. For example, excavation. Suppose we during the excavation we remove the soil. So, now if I remove the soil, then the stress on a soil is released. So, that means suppose we are removing soil up to height of h. So, that means this h total stress which is acting on a depth or height h below the ground level. So, that stress is removed. Now, if I apply the stress on that point, now that stress, if it is less than the previously applied stress on that point, then that is called as a over consolidated soil. So, now how I can determine that maximum past effective overburden pressure or the pre-consolidated pressure? That is very important, because we should know the soil that on which I am constructing or designing the foundation, the soil is normally consolidated soil or the soil is over consolidated soil. So, how that means we should know that which type of soil it is. So, that for to know that we have to determine what is the pre-consolidated pressure or maximum past effective overburden pressure. So, this technique is or this method is proposed by Casagrande in 1936. Now, what is the method? So, that means from the test we will get P E log P curve. So, this is also in log E log P curve. So, now the straight portion. So, if this is the curve, this is the loading portion, this is the unloading portion. In the loading portion, if this is the curve, so we will find a point where the curvature is the smallest radius of curvature. So, this is the point, O is the point where you can see this is the smallest radius of curvature, because you can see this curvature is changing, the radius of the curvature is changing for this curve. So, this is the point where radius of curvature is the smallest. So, we identify that point and then we will draw a line OA which is parallel to the x axis. So, draw a line OA which is parallel to x axis. Then I will then draw a tangent OB. This OB is a tangent at O. Then we have an angle AOB. Now, bisect this angle. Now, you extend this straight portion of the curve and it will intersect this bisection line. Now, this point corresponding to the stress is called the pre-consolidation pressure. So, this PC is very important, we have to identify this PC. So, that when you design we should know whether soil is over consolidated or normally consolidated. So, I explain these methods again. First, we will identify the point O which has the smallest radius of curvature. Then we draw a line OA which is parallel to x axis or the pressure axis. Then we draw a tangent at point O, this tangent BO at point O. Then we bisect the angle AOB, then extend the straight portion of loading curve and the intersection point between the extension line and the bisection line and corresponding stress of that point is equal to PC or pre-consolidation pressure. So, now we have this is the two cases. So, this is the normally consolidated clay, this is the over consolidated clay. So, you can see this is the loading part and the slope of that loading part will give the compression index, and then we have this is the PC and then we have a straight portion, and this is this portion is normally consolidated portion and this portion is the over consolidated portion. So, now we have to identify which portion the soil is. So, based on that we can determine the settlement of the soil. Now, if you have the, so that means based on that it has two cases, one is normally consolidated clay. So, if the soil is within that range, that means if the present pressure is greater than the PC, then the settlement we can calculate, that C c settlement we can calculate that C c 1 plus E 0 H log P 0 bar plus del P divided by P 0 bar. So, this is the expression. So, this expression you are getting from that Tazaki's 1D consolidation theory. I think these expressions is coming from the soil mechanics part. So, this expression, this term C c is compression index, E 0 is the initial void ratio, H is the thickness of, suppose this is the thickness of soil layer, H is the thickness of soil layer, and log this is base 10, and P 0 is the effective stress or effective overburden pressure, and del P is the additional stress which is applied due to the external loads. So, I will explain that how these stresses are calculated, how I will calculate P 0 bar, how I will calculate del P. So, when I will determine the settlement of the soil. So, this is these expressions, you just remember this expression. Later on I will come back to this expression, and I will frequently use this expression to determine the settlement of the soil. So, in that time I will in detail explain how I will determine the P 0 bar, effective overburden pressure, and del P for a particular foundation. Now, the thing that I am talking about, for the over consolidated clay, it has two cases. That one case is that the soil can be within this range and stresses. So, that means, here the initially P 0 bar is in this range, but when I apply the del P, then P 0 bar plus del P will be in this range. Another one, that P 0 plus del P both are in this range. For example, that one case is your P 0 and del P both are within this range. Another case, your P 0 is within this range, but P 0 plus del P is in this range. So, there are two cases. So, if there is two cases, so we can write that this is the first case, P 0 plus del P both are less than P c. So, we can get C c, instead of C c we will use C s, where C is the soiling index. That soiling index will get the slope from the unloading curve. So, we have a loading curve and the unloading curve. So, C c I will get from the slope of the unloading curve. So, for example, if I show you that, so this is the typical curve. So, C c I will get from the straight portion slope of the straight portion, and C s I will get from the slope of the unloading curve, or that is the soiling index. And if the case 2, P 0 is less than P c, but P 0 plus del P is greater than P c, then I will use these expression. So, these expressions are given. P c is the pre-consolidated pressure or past maximum effective overburden pressure. So, these are the equations I will frequently use, and then I will again explain how I will calculate these values in the during the design of foundation part. So, today I will finish this lecture 2 here, and then I will go for the shear strength part of the soil in the lecture 3, and we will discuss how the other parameters, which is the major important design parameters of the soil, that we will determine from the laboratory test, and what are the shear strength of the soil. Thank you.